This question is about the Fourier transform. We're given a time domain signal x of t. This notation simply means that x of t is the summation of x1 plus x2 plus x3, where each of these x1, 2, and 3 are given, and we're being asked to find the Fourier transform, x of omega. So what we need to find essentially is the Fourier transform of x1 plus x2 of time, obviously, plus x3. Now, using the linearity property of the Fourier transform, we can say that's simply the Fourier transform of x1 plus the Fourier transform of x2 plus the Fourier transform of x3, where each of these is given. So I will write this out line by line for each of these signals. So x1 of omega is the Fourier transform of x1 of t, which is given up here. So e to the negative 3t times u of t. And we can use the table of Fourier transforms where we're given that e to the negative at u of t forms a Fourier pair with 1 over a plus j omega. So we can write the answer as simply 1 over a plus j omega, where a in this case is 3, is the coefficient of t. So we can say x1 of omega is 1 over 3 plus j omega. So that's x1. Our next term is x2, which is a cosine. So x2 of omega is the Fourier transform of our next term, which is a cosine. And again, if we use the table, it looks like the answer is simply pi times an impulse at omega minus omega naught, which in this case, it will be the 4 pi. So omega minus 4 pi plus the same impulse at omega plus 4 pi. And our final term is a sum of 3 sinc functions. Now, if we look in our table, we do have a sinc function, but we don't have the Fourier transform of a sinc function. What we have is the inverse Fourier transform of a sinc function, giving you a rect function. So a rectangular pulse and a sinc function form a Fourier pair. So we can write that out like this. Rectangular pulse forms a Fourier pair with t times sinc t omega over 2. So if we wanted to find the Fourier transform of the sinc function, we would need to use the duality or symmetry property of the Fourier transform. So we could say that the Fourier transform of t sinc t omega over 2 would then be 2 pi multiplied by our rectangular function, but this time the independent variable, rather than being t, would be omega. So t and omega are interchanged. So let me write that as rectangular function of negative omega over t instead of t over t. So this is now our general form. Whenever we have a sinc function, this is what the Fourier transform will look like. So if we go back to x3 of omega, which we're trying to find, we can say that's the Fourier transform of our three sinc functions. So I can write that as my three sinc functions will be, let's write it like this, n sinc nt over 2, and that's from n equals 1 to 3. So that's our three sinc functions. So if we were to use our inverse Fourier transform or our newly found Fourier transform of a sinc function, we can say, using linearity and duality now, the answer would be 2 pi times a rectangular function with n equals 1, it'll be negative. The negative is unnecessary because it's an even function, so it's omega over t. T in this case is the coefficient of the sinc function, and that's going to be 1. So that's our first rectangular function. Our second will look very similar, but it will have a denominator 2, because we now have the coefficient here 2. So this n is this 2 because it would be the denominator in the rectangular function. So that's our second. And our third would look exactly the same, but this time we would have a 3. So it would be plus 2 pi times the rectangular function omega over 3. So the final step would be to write x of omega, because the question, remember, asked for the Fourier transform. So we need to write our final expression for x of omega as x1 plus x2 plus x3. So it's 1 over 3 plus j omega plus our two impulses at omega minus 4 pi and omega plus 4 pi plus our three rectangular functions. And I could probably write that again as a summation. N equals 1 to 3, 2 pi times the rectangular function of omega over n. So that will include all three rectangular functions. So there we have the Fourier transform x of omega. So the question goes on to ask for sketches of the magnitude of the Fourier transform of x1, x2, and x3. So if we remember that x1 is 1 over 3 plus j omega, then to remove the complex term from the denominator, we multiply numerator and denominator by complex conjugate. So that will give us 1 over 3 squared plus omega squared times 3 minus j omega. So if we wanted the magnitude of x1, then that would be 1 over 9 plus omega times the square root of 3 squared plus omega squared. And that will give us 1 over square root of 9 plus omega squared. So that's the magnitude of x1. And if we wanted to sketch that against omega, then it would look something like that. And at omega equals 0, we would have 1 over 3. So if omega was 0, it would be 1 over square root of 9, which is 1 over 3. So that point there is 1 over 3. So that's our first plot. The second plot is straightforward. The modulus of, or the magnitude of x2 of omega is simply pi of omega minus 4 pi plus pi omega plus 4 pi. And if we want to sketch that, then it will look something like this, x2 of omega. It will be simply an impulse with a height of pi, or an area of pi, at 4 pi, and then the same at negative 4 pi. And finally, x3 is what we found earlier. It's a summation of 3 rectangular functions. And if we were to find the modulus of x3, then it would be, or the magnitude, it would be the magnitude of these rectangular functions. And again, if we wanted to sketch this, it would simply look like three rectangular functions overlapping. So the first rectangular function would have a width of 1. The second would have a width of 1 over 2. So the first would have a width of 1 from negative 1/2 to 1/2. The second would have a width of 2 from negative 1 to 1. And the third would have a width of 3 from negative 3 over 2 to 3 over 2. And when you add those together, you end up with something that looks a little bit like this. Let me try to sketch this so it will look a little bit like this. So that's how you would add these sinc functions together in the time domain. So you stack the rectangular functions on top of each other. And you notice that the width of each rectangular function is increasing as the denominator increases. So that's how I would sketch the magnitude of the Fourier transform for x3. So the question then goes on to say, suggest a suitable sampling rate for x2 plus x3. So x2, that was the cosine. So that's cosine 4 pi t. And x3, that was the summation of sinc functions. And it specifically, the question specifically suggests that we refer to the sketch that we did in the previous part. So the sketch tells us the bandwidth for each of these. So when you're trying to sample, what you want is a frequency greater than or equal to twice the highest frequency. So actually, let's not say greater than, because the Nyquist rate is twice f max, but the sample rate will be greater than twice f max. So that means greater than 2 times the largest of, so the frequency of cosine 4 pi t in radians per second is going to be 4 pi, which is approximately 12. And then the sinc functions have frequencies of 1 over 2, 1, and 3 over 2. So the largest of these is clearly going to be the 4 pi. So the sample rate is greater than 2 times 4 pi, which is 8 pi, which is roughly 25 radians per second, because pi is 3.14. So your sample rate, if it says suggest a sample rate, we need to actually give it a number. So let's say a sample rate of 40 radians per second is suitable. And if we wanted to convert that to hertz, that would be 40 over 2 pi, which is approximately 6 hertz. And that's a suitable sampling rate. Why do we know it's suitable? Because it's greater than, it's considerably greater than the highest frequency amongst these two signals, x2 and x3. So that's how I would answer that part of the question. So the question goes on to ask for the spectrum of the sampled signal. So we need to sketch not x of omega, but the sampled version of x of omega. So let's call it xs of omega. So what does sampling do to a spectrum? It causes it to repeat itself at multiples of the sampling frequency. So if we take our sampling frequency to be a multiple of pi, let's say we take our sampling frequency to be 12 pi. So that's greater than 8 pi, so we're okay. Now remember, the bandwidth of our signal, our original signal, x of s, was 4 pi. So if we have 8 pi here, 12 pi, 16 pi, 20 pi, we can do the same on the negative side. Now remember, the spectrum needs to replicate. So let's first draw our original spectrum. That will look something like this. We have two impulses at 4 pi and negative 4 pi. And then we have this strange step where we have three rectangular functions stacked on top of each other. So 1, 2, 3. So maybe not exactly to scale, but that's what our baseband signal is going to look like. So after sampling, that is going to replicate, that's going to repeat itself an infinite number of times. So I'm going to try to copy this rather than to redraw it. So I'm going to have that replicated at multiples of our sample frequency. So it's going to be right there at 12 hertz, also 12 over pi radians per second, and at negative 12 over pi radians per second. And it does that an infinite number of times. Obviously, I can only draw the first few, but that's what it would look like. So because we're oversampling, that's why we have this gap here. So this is because we were oversampling. If we were critically sampling, then these two would overlap. And if we were, the impulses would coincide. And if we were undersampling, there would be an overlap and we'd have something called aliasing. So that's the spectrum. I just need to show that this repeats with these three dots there. And as long as you label your axis correctly, so this is in radians per second, and I don't label it as x, I label it as xs because it's been sampled. That should be okay. Maybe it would help if I labeled or annotated the y-axis with a pi there, and maybe a 3 there. That, and here a 3 over 2. That's as complete as it needs to be. The final part of this question is asking to find the integral of the magnitude of x of omega squared over all frequency. Now, this is a different signal. It looks a bit like a witch's hat. We don't know x of omega, so finding the integral of x of omega isn't straightforward. But if you remember from Parseval's theorem, the integral from minus infinity to infinity of the signal squared is equal to 1 over 2 pi, a similar integral in the frequency domain. And you'll notice that that is exactly what the question is asking for. So the question is asking for this without the 2 pi. So rather than calculating the Fourier transform and then integrating that, we can simply find the integral of x squared of t and then multiply that by 2 pi. Because x squared is given in the question. So we have the graph of x of t, so we can simply find x squared and integrate it. So that's the plan. So if we look at x of t, if we look at the signal, it is made up of 4 separate linear segments, and each segment can easily be written as a function of time. So we can say from -2 to -1, x of t is just a straight line with a gradient of 1. So I can say x of t is equal to t plus the y-intercept 2. So t plus 2. And if you look symmetrically at the other side, then here x of t has a gradient of -1 and y-intercept of 2. So it would be 2 minus t. And similarly, if we were to look at this segment from -1 to 0, then x of t has a gradient of 2 and a y-intercept of 3. So it would be 2t plus 3. And on the other side, it would be the same. It would have a gradient of -2 and a y-intercept of 3. So 3 minus 2t. And now we can put these together and find the integration of x squared. So the integral of x squared of t dt, we can write it as 4 separate integrations. So we integrate from -2 to -1 of x squared of t dt plus the integral from -1 to 0, and then from 0 to 1, and finally from 1 to 2. So this first integral I can write as the integral from -2 to -1, and the signal was t plus 2. So I'll just say t plus 2 squared dt plus the integral from -1 to 0 of 2t plus 3 squared dt plus the integral from 0 to 1 of what was it, 3 minus 2t squared dt, plus the integral from 1 to 2 of 2 minus t squared dt. So that's each of these separate segments integrated. And each of these is a direct linear integration, so that should be really easy to calculate. So I'll do that. So that's minus 2 to minus 1 of t squared plus 4t plus 4 dt plus from minus 1 to 0, 4t squared plus 12t plus 9 dt plus the integral from 0 to 1 of 9 minus 12t plus 4t squared plus 4 minus 4t plus t squared. So this is our first, second, third, and fourth integration. So now and if you calculate this one by one, you end up with 28 over 3. Now remember, that was 1 over 2 pi times the integral of x of omega squared. Okay, so that's what we found here. But what the question is actually asking for is the integral of x of omega squared. So we need to multiply by 2 pi. So our final answer will look like this. So either that or that. So that is your final answer.